Hi everyone. So in this video, we're going to talk about how we can use integration to find the volume of a three-dimensional object. So just a couple of things I want to mention. So this is probably one of the more challenging topics in this class. So I just want to kind of give you a heads up on that. I'm not saying that to intimidate you or anything, but just be aware that this is a topic that a lot of students find rather difficult. That being said, I'm going to try to make it as simple as possible and really break it down into digestible parts, but just be aware that this is a challenging topic. We're going to be spending quite a few videos on this topic, probably at least, probably like 5 videos total. So we'll see that there's multiple methods for finding volumes of three-dimensional objects. So we're going to cover one of those methods in this video, another method in the next video, and then in later videos we'll cover a whole different method. So just to kind of make a connection with what it is that we've been doing so far in this class. So far, we've been doing a variety of things, but in terms of, the physical meaning of an integral, we've been using integrals mostly to find area, right? To find the area that is bounded by a function. So far, we have been using integration to find areas. So I just want to kind of remind you where that, where the integral came from, this idea of like approximation and how that turned into the integral, because that same kind of connection is going to happen with talking about volumes. So when we were first talking about finding, the area of a region of a graph, we were using rectangles to approximate, right? So we would have something that looked kind of like this. And that would give us an approximate area. So the area can be approximated by adding up rectangles. So we would say that, okay, the area is approximately equal to the sum from 1 to n of f of xi times delta x. So I just want to remind you about what those different pieces mean. So this delta x refers to the base or the width of each rectangle. And then the f of xi refers to the height. Right, because you use the function to determine the height. So basically this kind of fancy summation notation is just a shorthand for saying, well, we can get the approximate area if we add up a bunch of rectangles. And so how do we find the exact area? Well, we took the limit, right? We thought of instead of adding up, 5 or 10 or 20 rectangles, we bring that number of rectangles towards infinity. So the exact area is what we get if we take the limit as n approaches infinity of that whole sum that we have written above. And so when you take the limit, that's what allows you to then turn it into an integral. So truly, when you're taking the integral from a to b of a function, that's the exact same result that you would get if you did this rectangle business and took a limit. And so I just want to remind you again of where the different pieces of the integral kind of come from in comparing with the limit definition on the left, because this will help us understand what goes on with volume. So the dx, where does that come from? That comes from this delta x, right? So that comes from the width of each rectangle. And then in the integral, we also have f of x, so that's just our function. And where does that come from? Well, that comes from the fact that for each rectangle, you have to find the height, and the height comes from the function, right? That's how you plug in an x value, and that tells you what the height is at that particular x value. And then the last piece here is that this integral symbol, well, that really kind of captures the idea of adding things up and adding infinitely many up. So you want to think of that integral symbol as a shorthand for this limit together with the sum. Okay, so now let's talk about volumes. So maybe before even getting into like the similar thing for volumes, what's the difference between area and volume? So area is a two-dimensional measurement, right? So when you're measuring the area of something, you can measure the area of a shape like a rectangle, a triangle, a circle, things that are a flat shape. So I just want to make it really clear that when we talk about volumes, we're going to be talking about three-dimensional shapes. So this is an example here of a drawing of a three-dimensional shape. Other examples of a three-dimensional shape would be like a box or a sphere or a cone, any three-dimensional shape. Those are the types of shapes where you can talk about volume. And so volume is like how much space something takes up rather than just like a flat measurement. So basically we're going to take this idea that we used up here and adapt it to now talk about volume. So similarly, we can use integration to find volumes. And so same idea with what we wrote down before. If you wanted to approximate the volume, how could you do that? Well, let's look at these two pictures. So this first picture on the left is just, it's some kind of three-dimensional weird blob shape. And notice the one on the right is basically kind of an approximation of the one on the left, but broken into like slices. Like it almost looks like a loaf of bread, right? So this is basically the same idea as using rectangles to approximate an area. We're going to use these slices to approximate a volume. So to approximate a volume, instead of adding up rectangles, we're going to be adding up, so maybe let me even add one more word to this. So instead of adding up the areas of rectangles, right? That's what we were doing in the area one. Base times height gives the area of rectangle. We'll be adding up, or we can add up the volumes of slices. So you want to think of slices as these, basically what you see in this picture on the right. Okay, so what is that going to look like in terms of, going back to this summation notation? Well, now we could say, okay, the volume is going to be approximately equal to, so we're going to be, basically what we want to put inside of this sum symbol is the volume of each slice, right? Because we want this to represent adding up the volume of the different slices. So how can we find the volume of a slice? Well, let's maybe kind of look at one of these. I'm just going to kind of do my best to draw one of these weird slices of bread, and I'm probably not going to do a great job, so I apologize. Okay, so let's say that this is one of the slices that is in here, right? So I'm just kind of pulling this out. So how would you find the volume of something like this? Well, notice that it has a uniform thickness, right? So the way that this is sliced, every piece has the same thickness, and it's a uniform thickness all the way throughout the shape. And so we can call that thickness delta x. And so what would we need to multiply with delta x in order to get the volume of this slice? We would need to multiply the area of this face. Right? If you multiply the area of a two-dimensional object by another dimension that is thickness, that will give you the volume of the shape. It's kind of like if you have a box and you do length times width, that gives you the area of a rectangle, and then you multiply that by height, and that gives you the volume of the whole box. So it's a very similar idea. So what we're going to put inside of this sum is a of xi times delta x. And again, what does this represent? Well, the delta x represents the thickness of each slice. And then the AXI represents the area of, I'll say, the ith slice. Because as you can see in the picture, and maybe actually, I'm not going to use the word slice here, I'll say cross section. So when I say cross section, I mean basically just if you look at the slice and you just look at its face and find the area of the face, that's what I mean when I say the ith cross section. Because as we can see by looking at this picture, if you were to look at all these different slices of bread, they would have different sizes on the face, right? The thickness is the same, but the size of the face is different. And so that's why I'm saying the area of the ith cross section. So if we wanted to find the exact volume, we're basically just going to use the exact same idea that we used above. So the exact volume is going to be now taking the limit. The limit as n approaches infinity of the sum from 1 to n of a of xi delta x. So what is this going to become? Well, just like we saw above, the limit together with the sum, that becomes an integral. So it's going to be the integral from a to b, and we'll see later on where that a and b come from. I mean, basically just if we go back up to this this picture, we can see that we're positioning our object that we're trying to find the volume of. We're positioning it between two different x values, and so that's going to be kind of what determines the bounds. But we'll see more of that later. So we saw that above, that became the integral symbol. And then what is a of xi going to become? Well, that's just going to become a of x. So it's going to be some kind of an area function. And we'll see how that plays out in our examples in a little bit. And then delta x, as we saw above, that's going to become dx. So this is a really important formula. And this is something we're going to be using basically in the next few videos. So this idea that you can find a volume by taking an integral of an area function dx. And so again, in order to remember this and not have to just memorize it, I think if you can think back to this picture and just think about, okay, how would I add up all these different slices? Well, I would need to multiply the area of each face times the thickness, and that's where this a of x times dx comes from. Okay, so this is one example of what a volume could look like. And we will do some examples in this class that are kind of more funky shapes. But for the most part, we're actually going to be focusing on one really specific type of volume that actually isn't really going to look like this one here. So I like to kind of talk about this general situation so that later on, when we get back to other types of volumes, you have something in mind. But for the next few videos, we're going to be focusing on a type of shape that's called a solid of revolution. So let me describe what that means. So for the most part, in this class, we will be focusing on finding the volumes of shapes called solids of revolution. So what is a solid of revolution? It's basically a shape that you get by taking a region in the xy coordinate plane and revolving it around a line. And so for the most part, we're going to be revolving these shapes around either the x or y axis, but there might be some exceptions to that. And we'll actually see one exception in this video. So let me just draw a quick sketch, and then we'll get into an example of a specific example. But so one example of how a solid of revolution could look is, let's say you have a region that looks like this in the xy coordinate plane. Oops. And if you take this region and you revolve it around the x-axis. So what does that mean? What do I mean when I say revolve this region around the x-axis? Well, I'll show you a video. I think that might help you visualize this in a moment. But basically, I want you to picture this purple region rotating out of the page towards you and around in a circle. And so the resulting shape is going to kind of look like a bell. So it's going to kind of come down and look like this from the side, but it's a three-dimensional shape. So I'm going to add this kind of circle to emphasize that. So we're talking about, when we're talking about solids of revolution, we're talking about taking a two-dimensional shape and spinning it around to give you a three-dimensional shape. So this would be an example of a solid of revolution that is revolved about the x-axis. And we can also do them around the y-axis. So let me just sketch an example of what that might look like. So if you have, some shape that looks like this, so we have this two-dimensional shape. If we take that and revolve it now around the y-axis, well, it's going to give you a similar looking shape, but this time positioned the other way. So it would look something like this, again, kind of like a bell shape. So this would be one that goes about the y-axis. And so the really important thing to realize about these solids of revolution, and again, I'll show you, I think when we look at something, this video and then this other thing, you'll be able to really see this for yourself. I want you to think for a moment, if you take a shape like this and you revolve it around in a circle around either the x or y axis, what will it look like? Like what shape would you see if I were to cut into it like right here and turn it towards you? What kind of a shape would you see? So it would be circular, right? Because the way that you're creating these objects is by swiveling something around in a circle, the cross sections are going to be circular. And so that's going to be really important because when we do this process of looking at the areas of the cross sections, they're not going to be like weird bread-shaped blobs. They're going to be circles. We're going to be looking at circular slices. And so you might have noticed I wrote at the top of this page the disk method. Basically, the reason that the method we're going to be using in this video is called the disk method is because when you take a solid of revolution and slice it, you're going to end up with these shapes that look like disks, right? Sometimes I like to describe it as pancakes. So let me just write that fact down, which is that the cross sections of solids of revolution are circular. So that's going to be a really important fact. Okay, so I want to get into an example. And so just to let you know how the rest of this video is going to go, we're going to do 4 examples. So the first 2 are going to be like relatively straightforward, kind of similar examples. And then there will be 2 more that both get into something a little bit different. Okay, and we'll use this first example. Once we do this first example, I'll also write down kind of what the general method or formula is, but I want to kind of do it by an example first to really help you see where the formula is coming from. Okay, so I'm going to write down the problem statement here, and whenever you write down these problems, you'll see they're kind of wordy. There's a lot to write down, so I'll help you understand exactly what this question is asking. So find the volume of the solid obtained by revolving the region bounded by y is equal to square root of x, x is equal to 0, x is equal to 4, and y is equal to 0 about the x-axis. Okay, so there's a lot of words here, and there's basically kind of 2 parts to this question. So the first thing you want to focus on is figure out what's the region we're talking about, because just like these 2 examples above, you're going to start with a 2-dimensional region and then you're going to rotate it. So you first need to figure out what is that 2-dimensional region. So look for the word region bounded by. So the region bounded by these things. So that's the first thing that we need to kind of illustrate. So I already have the graph of y is equal to square root of x graphed here. So let's put in the other parts. So we're also supposed to have x is equal to 4, and x is equal to 0 is already kind of the end of this, so I'm not going to put an extra line there. And then y is equal to 0. So this is our region. And so, by the way, this is why we do that section about the area between curves before doing volumes, because hopefully you now have some practice with, reading this list of equations and being able to understand, what is that region we're talking about. So you're always looking for the region that it falls in between all of the different things described. Okay, so now we're supposed to take this shape and revolve it around the x-axis. So I'll sketch this in a second, but first I want to just pull up a couple of resources to help you really visualize what's going on here. So the first one is just this video. This is a really short and kind of not super high quality video, but I think it's the best I've seen for just literally showing what I'm about to do. So notice there's a two-dimensional region in the XY coordinate plane. And what's going to happen is they're going to show in two different ways. They're going to show what it looks like to take this region and revolve it around the x-axis. So that's kind of one view of it. And now they'll do like a more solid view. So notice that we get this three-dimensional shape, and you can picture that if you were to take this and turn that blue end of it towards you, it would be a circle. So this is what we mean when we say we're revolving around the x-axis. We mean, we're doing a motion like this. Okay, I want to show you one other thing, and this is a really cool tool, and I'll link this on Canvas. It's a little glitchy just because I think it is kind of computationally intensive. But basically what you can do is you can type in what your function is. So I did square root of x. I put in my bounds 0 and 4. And then notice that it's currently approximating that area with rectangles. So I'm going to now do something where I spin these rectangles around, and what you'll see is it's going to give us a picture that actually looks a lot like this picture with the slices of bread. So we're going to see what it looks like to have our volume kind of cut into these discs, these circular slices. So I'm just going to spin these rectangles around. So we can see that, it's not a perfect representation of the volume, but we can see that it kind of approximates that volume, right? And the one thing I really want to emphasize is if I turn it this way, it's circular, right? So all of those cross sections are circles. And then what we can do is, and once you do this, it kind of freezes up because I think, again, it's too much computing power. So I'm going to increase the number of rectangles so that you can see how the volume becomes a better approximation. But once I do that, I don't think I'll really be able to spin it or move it around anymore. So I'm just increasing the number of rectangles. You can see that, that now all of a sudden the volume looks a lot more accurate. So that's really the idea that's underlying what we're doing here, is just like when we're finding areas, it's like we're using infinitely many rectangles. When we're finding volumes, it's as if we're using infinitely many of these little pancakes, slices. Okay, so let's get back to this problem. So I'm just going to draw a rough sketch here, and it's really, really important that you draw pictures for these. I know not everyone is an artist or maybe feels super comfortable drawing, but I on a test or quiz may ask you to actually draw some of these things because I think it's really, really important. And we'll see in some later examples, the more complicated these get, the more important it is that you have a picture to refer to in order to really figure out what you need to integrate. So when I draw these pictures, usually what I do is I start by drawing kind of the side view. So I just take whatever that region is and I just kind of flip it over. So this would be like what it would look like from the side. And then you don't have to do this part. Some students don't. I like to just kind of add this circular shape just to kind of emphasize the fact that it's three-dimensional. Okay, so how are we going to find the volume of this thing? Well, we saw on the last page that we want to do an integral of an area function. So what is that area? That area is the area of each slice, right? We're picturing that we're adding up a bunch of slices. And so I'm just going to draw kind of a random slice in the middle of this. So if we were to slice this, we would get a little piece that looked like this. So I'm going to make it kind of look like picture like a pancake. So if we had to figure out what the area is of that slice, so why am I saying area and not volume? Because we already are multiplying by dx, right? That takes care of the thickness, and that's why we just have to focus on area. So how would we find the area of this cross section? Well, it's a circle. right? Because as we saw in the last example, like if you were to rotate this, it's circular. So in this case, the area, so let me say it this way, the slice or slices are circular. So how do you find the area? Well, the area of a circle is pi r squared, right? And so basically what we need to do is calculate our volume by taking some kind of an integral of pi r squared dx. So again, just to remind you, where is all of this stuff coming from? The pi r squared is the area of the slice, the dx is the thickness of the slice, and then the integral symbol represents the fact that we're adding up a bunch of slices. So now all we have to do is look at our picture and basically figure out how you would go about calculating the radius. And so this is why drawing a picture is so important. So I'm just going to put in a little green line there and label that with R. So that's the radius of our circular cross section. And we basically just need to figure out, how would that radius be calculated? So what I mean by that is think about going to a particular x value. So right now, the way I drew the circle, we're on an x value of 2. So if we needed to figure out what that green distance is when x is equal to 2, what would we need to do? Well, we would need to plug it into this graph, right? Like this graph is y is equal to square root of x, right? And so if you were asked to find this green distance, that green distance would just be square root of 2 in this case, right? Or if you wanted to find the distance here, it would be square root of 3. Or if you wanted to find the distance here, it would be square root of 1, which is 1. If you wanted to find the distance here, it would be square root of 4, which is 2. So no matter what x value you're on, the way that you find this radius, which is the same as the height of the function, is just by taking the square root. And so in this case, so I'm going to replace this with green just to really emphasize what we're doing here. So I'm going to pull the pi outside of the integral, and that's what we're generally going to want to do. And I'll just leave a and b for now, and we'll come back in and change the bounds. So I'm going to replace r with the square root of x, right? Because that we just said that was how you could actually find the radius. And so then what are the bounds? Well, the bounds are just going to be what is the very smallest x value at which we'll be making a slice, and what's the very biggest x value at which we'll be making a slice. So the smallest one is 0, right? Like if you were to go through and draw more of these slices like the one I drew, the very first one would be at 0. And then where would the very last one be? It would be at 4. And so now we're actually ready to calculate this integral. So we have pi times the integral from 0 to 4, and we have square root of x squared, which is just x. And so now we just want to find the antiderivative of x, which is x squared over 2, and evaluate it at 4 and at 0. So when we plug in 4, we get 16 over 2. And when we plug in 0, we just get 0. So I'm going to stop at this point, always writing down minus 0. If the function, your antiderivative, is a polynomial, so if it only involves powers of x, you can just assume that when you plug in 0, you just get 0. Just be careful because there are functions like e to the x, for example, or cosine of x, where when you plug in 0, you don't get 0. So I don't want you to assume that plugging in 0 always gives you 0. But if you can recognize for a specific function that it does, then great, you don't need to write that part down. Okay, so our answer is 8 pi. That is the volume. And if we were having units, they would be cubic units, right? We're talking about space. So just to summarize, what did we do here? We took this idea of integrating an area function and we made it specific for this type of situation because we said, well, in this case, the area of the cross sections are going to be circles. And what's the area of a circle? It's pi r squared. And then we figured out what the radius was by looking at our drawing and looking at what functions were involved and just using that to and common sense to figure out, what is our radius. So this is going to be the general method for volumes of revolution like this. So I just want to kind of write this down as a general fact, because this is kind of, if you're looking for what's the formula you want to know, it's this next one. Okay, so in general, if a solid of revolution is revolved about the x-axis or a horizontal line. So we'll see an example at the end of the video of where you revolve something around a line that is not the x-axis or y-axis. Then its volume, and we'll also see that there's a different equation for around the y-axis. We'll get there in a little bit. So the volume is going to be pi times the integral from a to b of r squared dx. So where do these different things come from? Well, as we talked about above, r is basically determined by your function. And so I don't want to just say that r is necessarily just equal to, I'll say it like this. I'll say r is determined by the graphs in, I'll just say in each situation, because I just want to be really careful that, so in the example that we just did, it was true that the radius was just equal to y is equal to square root of x, right? It was equal to like our main function in the problem, but that's not always going to be the case. So I don't want you to like think that that is the rule. It really depends on your situation. So that's why I'm saying it's determined by the graphs in each situation. You just have to draw a picture, kind of really see what's going on in that situation. And then the bounds are basically going to be the x values of the first slice is the lower bound, and then the top bound is the x value of the last slice. So just like the example we saw above. And I like to pull the pi outside because it just makes the integration a little easier, but I do want you to remember, where does this come from? It comes from the fact of pi r squared being the area of the cross section, and then we're just pulling that pi outside. Okay, so we're going to do, like I said, 3 more examples. So the next one is going to be pretty similar to the one that we just did in terms of its kind of simplicity, but then we're going to get into a couple of more challenging examples. So the first example is we're going to find the volume of the solid obtained by revolving the region. I always wish there was like a faster way to say this, but there just isn't. Bounded by y is equal to 1 over the square root of x minus 1. Y is equal to 0. X is equal to 2. And x is equal to 4. And again, we're going to do that about the x-axis. So again, the first thing you want to do is focus on figuring out what's the region you're talking about. So it's supposed to be the region bounded by these graphs. So right here, I have the graph. This is y is equal to 1 over the square root of x minus 1. So then we need to add in y is equal to 0. So that's just the x-axis. And then we're supposed to be between x is equal to 2 and x is equal to 4. So this is the region that we're looking at in this case. And then we want to revolve this region about the x-axis. So what kind of shape is this going to give us? Well, again, I'm just going to do first this 2-dimensional view. And I found that a lot of students kind of prefer to probably just leave your picture as the 2-dimensional view, and that's fine as long as you kind of understand that it is actually a 3-dimensional shape. Because I think I know it can be a little confusing to have kind of simultaneously the 2-dimensional and 3-dimensional shape at the same time. What I do think is important, though, is to be able to draw in this sample slice. So here is a sample slice. I just like to add like a little thickness to it just to represent the fact that, you know, it's not just a circle, it's actually like a slice. Okay, so how are we going to find this volume? Well, we're going to use the exact same approach we did in the last one. So we now know that we can find the volume by doing the integral from a to b of, and so we need to figure out what our radius is, squared dx. So to find the radius, we want to go to our slice and draw the radius in for that and just figure out, you know, if I'm at a particular x value, what would I need to do in order to figure out that radius? And so you can even pick a specific number. You can pick like 2 or 3 or 4 or any number you want between 2 and 4 and just figure out, you know, what would I need to do in order to figure out the height or the radius. And so in this case, you would just need to plug it again into this function, right? Like for example, if you're trying to find this radius here, if you plug 2 into this function, you get 1 over the square root of 2 minus 1, and that's 1. And that's exactly the radius we see here. And so if you wanted to find the radius at a slice that was at x is equal to 3, then you would plug in 3, and you'd have 1 over square root of 2. So wherever you are, you know, whatever x value you're choosing to do your slice at, it's always going to be the case that you can find the radius by just plugging that into this function. And so what we're going to do is we're going to replace where we wrote r, we're going to replace that now with what we just said r was, right? So we're going to replace it with the function 1 over the square root of x minus 1. And then what are the bounds? Well, in this case, the very first slice is going to happen at x is equal to 2, and the very last slice is going to happen at x is equal to 4. Okay, so this simplifies, right? Because when we square it, kind of like in the last example, the square root is going to go away. So we're just going to be left with 1 over x minus 1. So how would we find the antiderivative of this? Well, you could use u substitution. You could set u equal to x minus 1, but this is going to be an example where I think it would be helpful if you don't rely on u substitution. So I want to kind of go off to the side for a second and just show you something in general. So if you're using the chain rule, so I'm talking now about taking derivatives, or maybe let me say it this way. So if you are taking the derivative of a composite function where the inside function is just x plus or minus, I'll just say x plus c, where c could be a positive or a negative number. Basically, when you use the chain rule, the inside derivative is just going to be 1, so it's not really going to contribute anything. So why am I telling you this? Well, basically, let me give you a few examples. So if you had, let's say you were trying to take the derivative of e to the x plus 5, well, the derivative would just be e to the x plus 5 because you would use the chain rule, but the multiplying by the inside derivative would just be 1. So you would just say, oh, it's just e to the x plus 5. Similarly, if you take the derivative of, let's say, cosine of x minus pi, well, that would just be, so the derivative of cosine is negative sine of x minus pi. Or just to pull it back to now the example we just had, if you take the derivative of ln of x minus 1, well, that would just be 1 over x minus 1, right? Because the inside derivative would just be 1. So my point in telling you this is that when you're taking the antiderivative of something that looks like this or like this or like this, you don't really need to use u substitution because you can basically just take the antiderivative normally and just leave your input the same as the input in the function you're taking the antiderivative of. So specifically, the example that we're integrating here is 1 over x minus 1. Right? That's what we're trying to take the antiderivative of. We just said down below here that the derivative of ln of x minus 1 is 1 over x minus 1. And so that means that the antiderivative of 1 over x minus 1 is ln, and we should put absolute value bars here when we're taking the antiderivative. So it's going to be ln of absolute value of x minus 1. So you're welcome to use u substitution. I guess all I'm trying to say is that it's really not necessary, and I think it might just kind of complicate things a little bit. So we can just know that the antiderivative here is ln of absolute value of x minus 1, evaluated at 4 and at 2. And so that gives us, if we plug in our numbers, we have ln of 4 minus 1 minus ln of 2 minus 1. So that's going to be pi times ln of 3 minus ln of 1. And then ln of 1 is just 0, because it's asking you what power do you need to raise e2 to get 1, and the answer is 0. So we're just left with pi times ln of 3. And that would be our final answer, because that would be an exact form. You know, just like with the other ones, you could get an approximation by typing this into a calculator, but this would be kind of the preferred answer. So let me just kind of put a bubble around this. This is just kind of like a side note, but I think it's an important observation that will save you time when you're dealing with antiderivatives of things that are composite functions, but basically kind of simple composite functions. Okay. So next up, we're going to look at an example where we're revolving something now around the y-axis. And we'll see that basically it's almost an identical process. It's just that we're now going to be integrating with respect to y instead of with respect to x. So this time we're going to find the volume of the solid obtained by revolving the region bounded by. So we have y is equal to square root of x. Y is equal to 2. What else do we have? X is equal to 0. I think that's it actually. And x is equal to 0. And we're now revolving it, like I said, about the y-axis. Okay, so that means that we have this region here. So x is equal to 0, y is equal to 2. So we're looking at this region here. And we're revolving it about the y-axis. So that means we're revolving it around here. So let me draw, again, that kind of two-dimensional shape first, and then I'll add a little bit of a three-dimensional look to it. This one is a little tricky because it's such like a wide shape. But, you know, it looks kind of like, I don't even know, like one of those really short traffic cones, but upside down. Okay, so why are we going to need to do things differently in this case? Well, if you think about why was it that we were integrating with respect to x in these earlier cases, so maybe this is like the easiest illustration to see. So why were we integrating with respect to x in this case? It was because the thickness of this slice was delta x, or actually, let me just say it as dx, right? So that was really where the fact that we were integrating with respect to x came from, because the slices, their thickness was measured horizontally, right? It's a change in x. Whereas if we look at this example, now if you look at a sample slice, and if you were to measure the thickness of that slice, well, now that thickness of that slice would actually be delta or dy, right? Because it's a change in y, it's a vertical thickness. And so that's kind of the clue that we need to revolve, or what we need to integrate with respect to y. And additionally, the rule that you can just kind of think of is if you're revolving it around the x-axis, you're integrating with respect to x, and vice versa. Although we'll see that that same rule isn't going to be true when we get to other methods in the future. But as long as we're talking about the disk method that we're working on now, that will be true. Revolving around the x-axis, you integrate with respect to x. Revolving around the y-axis, you integrate with respect to y. Okay, so other than that, just like change, it's going to be really the exact same situation. So we're still going to be integrating something from a to b of r squared. The only difference is that now it's dy. But that does mean that there's something we're going to have to change, because we need to make sure that r can be expressed as a function of y instead of as a function of x. So if we look at this picture, the curve that is determining the radius is this one, right? And we earlier were given this one as y is equal to square root of x. But we need to change that around and rewrite it as a function of y. Because then, for any different y value you go to, you can figure out what this distance r is. So what would this be as a function of y? Well, we just need to solve it for x. So that would give us x is equal to y squared. And technically, x is equal to y squared would also have like the second half of the parabola, but it's okay because we're focused on this half of it anyway. So because of the bounds, it's really not going to matter that you're only looking at part of that parabola. So let's just kind of double check that makes sense. So for example, if you're at a y value of 1 and you want to find what this distance r is, you would just plug it into this equation. So you'd say x is equal to 1 squared, and that's exactly what this radius is, right? This is a radius of 1. Or if you wanted to find this radius at a height of 2, you would say x is equal to 2 squared, and you would get 4, and that's exactly the length of this radius up here. So it is the correct equation. And as I mentioned earlier, you can always check, just check, like pick a specific x value and make sure that when you put, or in this case, y value, depending which way you're integrating, plug it into your radius equation and make sure that actually gives you the right radius. Okay, so we're going to now replace where we have an r, we're going to replace it with y squared, because that's what we just figured out that, that r was equal to. And then what are our bounds? Well, similarly, we're just going to be picking the first and last y value that kind of makes sense in this problem. So the smallest y value is 0 and the biggest y value is 2. And so this is going to become pi times the integral from 0 to 2 of y to the 4th dy. And so if we take the antiderivative, we end up with y to the 5th over 5, and we're still multiplying by pi, and we're evaluating y to the 5th over 5 at 2 and at 0. So when you plug in y to the 5th, when you plug in 2, you get 32 over 5, and as we mentioned earlier, we're just going to get 0 at the lower bound, so we're left with 32 pi over 5. Okay, so let me just write down this kind of general fact so that when, if you're looking back at your notes, you have it similarly that we did for x. So when finding for a solid of revolution revolved about the y-axis, or a vertical line, the volume is going to be, again, pi times the integral from a to b of r squared dy. And really the only difference other than the dy is the fact that these bounds have to be y values, right? And then the radius has to be determined as a function of y. So just kind of makes sense, right? It's kind of like what we talked about with substitution, that whatever variable you're using, everything should kind of match up. So you want to make sure that when you're integrating with respect to y, your radius is determined as a function of y, and your bounds are also y values. Okay, last example. So this one is going to introduce something a little different, a little tricky. So in this case, we're not going to be revolving around the x or y axis. We're going to be revolving around a specific line. So in this case, we're going to be finding the volume of the solid obtained by revolving the region bounded by. So this time we're working with x is equal to y to the fourth, x is equal to 0, and y is equal to 1. And we're going to be revolving about the line y is equal to 1. So let's start by looking at our region. So this graph here is the graph of y is equal to, x is equal to y to the fourth. So it's like a sideways, not a parabola, but a sideways version of y is equal to x to the fourth. And then we have x is equal to 0, so that's here. Let me make that a little better. And then we have y is equal to 1. So we have basically this kind of region here. But instead of revolving it around the x or y axis, we're going to revolve it around this line. So what that means is that, you could even picture, like, just imagine now that this is the x-axis and kind of do the same thing we did in the other problems. So what it's going to look like is it's going to now have, another side of it like that. And if we were to add this kind of three-dimensional shape, which is, in this case, I think a little tricky because it's the bottom is very flat. But, it would look like this. Again, it looks kind of like a cone shape. So how do we go about finding the volume of this? Well, again, it's going to be the same equation. The only difference is that now when we go to find the radius, it's going to be a little bit trickier. You can't just assume that you're going to use your function. You have to actually look at your picture and kind of analyze what's going on. And that's why drawing the pictures is so important. So we have pi times integral from a to b. We're going to want r squared. And we're integrating with respect to x, right? Because we're revolving around a horizontal line. And if you were to draw a sample slice here, the thickness of this slice would be delta or dx, right? Not dy, because it's a horizontal thickness. Okay, so what is going to be the radius in this case? So let me label this with r. So there's one thing actually we need to do before that, which is, even though the radius is not going to just be equal to this function that's graphed, there's going to be a little more complication. We do need to change this function to be as a function of x instead of a function of y, right? Because we're going to be integrating with respect to x. So currently it's written as y is equal to x to the fourth. So how would we write that as a function of x instead of as a function of y? Well, that would be the same thing as y is equal to the fourth root of x, or we could write it as x to the 1/4. So that's going to be the equation we're going to be using. Okay, so how would we go about finding this, this radius? Well, let's think first about, what is y is equal to x to the 1/4? What distance would that give you? That would give you this distance, right? This would be like, if you plug a particular x value, let's say that we're at like 0.4. If you were to plug 0.4 into the function y is equal to x to the 1/4, that would give you this distance in orange, right? So this distance here is x to the 1/4. Like, forget, maybe cover up the part that's shaded in now to really convince yourself of this. Like, anytime you're plugging in a number to the function, it's just giving you the distance from the x-axis to the function, right? And so what we're looking for is that distance in green. So the other observation we want to make here is that if we were to measure the distance all the way up like this distance, and maybe let me do it this way, this distance would be 1, right? The distance all the way from the x-axis up to 1 is a distance of 1. So how could we figure out what r is? Well, looking at this picture, we can tell that r plus x to the 1/4 is equal to 1. Right? Just, we're not really doing calculus here. We're just kind of looking at a picture and doing some geometry, just kind of adding things up, making sense of them. And so how would we find r? Well, r would then have to be equal to 1 minus x to the 1/4, right? And so that's what we're going to be plugging into our function as r. So this, again, is why it's so important that you draw a picture and actually kind of make sense of what's going on rather than just blindly grabbing a function and plugging that in for r. You know, that will work in some cases, maybe you might get lucky, but in some cases it won't. So it's really important that you draw a picture and just try to really get a grasp on what's happening in that specific situation. So we're going to replace where we had r, we're going to replace that with 1 minus x to the 1/4. And our bounds are going to be, so our smallest x value is 0 and our biggest x value is 1. Okay, so now we want to actually expand this out, right? So if we have 1 minus 1/4 or x to the 1/4 squared, we can multiply that out. So that would give us 1 minus 2x to the 1/4 plus x to the 1/2, right? If you were to multiply x to the 1/4 times x to the 1/4, you would add those exponents up and you would get x to the 1/2. So that would give us, as our, maybe I'm going to go down here to kind of give us a little more space. So the antiderivative would be, so we have still that pi on the outside, and then we have x minus, so we're going to have 2 times, and I'll leave a little space here to put the new coefficient. So the new exponent would be 5/4, right, if we add 1. And so that means that we're multiplying by 4/5. And then the next new exponent would be 3/2, and so we need to multiply that by 2/3. And we're evaluating at 1 and at 0. So always nice when we're evaluating at 1 and at 0, because those are like the two easiest numbers to plug in. So we're going to, for the first one, we'll just have 1. For the second one, we'll have 8/5 times 1, which is just 8/5. And then for the last one, we'll just have 2/3. And then if we were to plug in 0, we would just get zeros everywhere. So we don't need to do that one. So almost done here. So let's make a common denominator. So we have 15/15 minus 24/15 plus 10/15. And so this is going to simplify to pi times 1/15, which can also be written as pi/15. All right, so that is it for this video. In the next video, we're going to learn a different method that's basically for finding volumes of shapes that have a hole in the middle. So in order to make this topic, like I said, it is a really challenging topic. So in order to make it really digestible for you, I would really recommend that you do the homework related to this video sooner than later to kind of practice. And then you can do the ones related to the next video later, just because otherwise you're going to have a lot of volumes problems to do at once. And I think it might get kind of overwhelming. So I'd really recommend breaking it up, doing the ones related to this stuff first, and then doing the other ones later.